Hi everybody, and welcome back to this course. I mean, if you observe maybe a bit closer, you will see that it's not exactly the same location as where we were before. I mean, a few months have passed, I'm a bit more tan, and also, I mean, right now we are not in Nice anymore, we are in a beautiful place called the Math Village, which is in Turkey, close to Izmir. And so I have the pleasure to record part of this course, I mean, here in the Math Village. So let me remind you that, as usual, I mean, this course, I mean, that we are recording now, should not be considered as alone. I mean, it should be seen as like a complementary part of the notes of the course that already exist. So when you're watching it, each time keep in mind that it is like something to help you understand a bit better the notes of the course that I will refer to most of the time. And so what are we going to do during the next lectures? After like doing a lot of geometry of curves, we have like study in particular Riemann theorem and how it helps us to try to have like good models of curves. Now we are going to turn to the arithmetic part of the curves. And there is one main theorem that we have to look at when we speak about curves over finite fields and the number of points, and they are called the Veil Conjectures. So I'm going to explain what the Veil Conjectures are. I'm going to also show you a couple of examples and consequences, and then I'm going to give a proof of the Veil Conjectures, at least part of it. And it will be a different proof that there is in the notes. As you will see, I mean, it's a completely different proof. I mean, the spirit is really different. But I think that it's a very important theorem, so it could be nice and interesting for you to have like two different proofs of this theorem. So let me start by explaining a bit more this Veil conjecture. So as usual, we start with a curve C over FQ. So C, let me remind you, is going to be smooth, projective, and absolutely irreducible curve of genus G. And the definition of what is called the zeta function of the curve that we will denote Z, C over, so this field I'm also denoted K from time to time. So it's a power theory, and it will be a bit strange maybe at first sight, because it's an exponential of a sum from n1 to infinity. Here you put the number of points on the curve over a degree n extension, and you multiply it by t to the n over n. So somehow what you already observe here is that this power theory is going to contain all the information on the number of points on the curve, not only over FQ, but over any kind of extension. So it's really powerful somehow. It really contains a lot of information. So, but then, I mean, you could have said, why didn't you just put sum of this times t to the n? I mean, there is one reason first, I mean, but let me show you on an example what it does if I take the case of P1. So if I take P1, we know that the number of points over any extension of P1 is q to the n plus 1. And now if you plug this inside this formula, what you observe is that this is going to be exponential. And now what you recognize are some power theory related to log of 1 minus t and 1 minus qt. So this is minus, more exactly, 1 over t minus log of 1 minus qt. And of course, then what you get is 1 over 1 minus t, 1 minus qt. So, rational fraction. Nice. So it seems that indeed maybe it helps to put it in this way. And this is really what the Veil conjecture for curves because there are Veil conjectures for any kind of variety. So this one were proved by Veil in 1941. Actually, there is quite a big story behind this proof of the Veil conjecture, because there is a controversy between Veil and Haas, who was a German mathematician, and of course it was a war, so yeah. I'll let you read about this interesting piece of history of math, but let me just state what the Veil conjectures are. So there are three parts. The first part is that it's not an exception what we saw for P1. The zeta function is always a rational fraction. Then there is something which is called the functional equation. That says that this, when I replace t by 1 over qt, it is related to the original zeta function up to the power of this form. And then the most important piece, let me do it like this then, is 3, what is called the Riemann hypothesis. In this context, of course, not over number fields, which says that there exists a polynomial with integer coefficients, such as the degree of f is 2g, and I can write f in this way. F of t is going to be a product from e equal to 1 to 2g of 1 minus alpha I t with, and this is really the most important part, the norm of alpha I is square root of q, such that, how is it related to the zeta function? Well, the zeta function of the curve over k in t is f of t divided by 1 minus t, 1 minus qt. Okay? So for P1, that was genus 0, so we had like a constant, and this constant was just 1. And more generally, so we have a polynomial of degree 2g. And if you look at it, it's really important because it says that somehow, the arithmetic of the number of points on all extensions is ruled by the arithmetic on the 2g first extension. Because if you know the number of points on the 2g first extensions, then you determine f of t. This is known, and then the number of points over any extension is known. We will see an example later. But maybe let me first comment why this is called the Riemann hypothesis. So if you let the function zeta like this be, let me replace t by q to the power minus s, then you see that the zeros of zeta of s, c of s, have a real part equal to 1/2, which of course reminds you of the classical Riemann hypothesis that we have for Q. And you see, the difference is that in this case, this is a theorem, and in the other case, it's still like a long-standing conjecture. And as another remark, let me rephrase also 1 plus 2 plus 3 in one way of writing the zeta function. So instead of writing so the zeta function of c k t is going to be a rational fraction, so 1 minus t, 1 minus qt. And in the numerator, what I will do is put the roots in this way. what the functional equation tells you is that you can always put the roots together in this way. So 1 minus alpha I t, and all the time you have the conjugate root. Okay, so you can also write the expression like this. And sometimes people write the root alpha j in the form square root of q times exponential I alpha j with an alpha j which is between 0 and pi. And these values are exponential I alpha j are called somehow the eigenvalues of the Frobenius, and yeah, they have important like distribution properties that are studied a lot. Okay, that was for a remark. Let me also maybe state a corollary. Is that if you take these formulas and you look at what it says for the number of points, you can see that you get that the number of points over any extension is given by 1 plus q to the n minus the sum from e equal 1 to g of alpha I plus alpha I bar. Okay? So very nice formula, and as a consequence also we have that if I do the number of points of every extension fq to the n minus 1 minus q to the n. So this is this sum here, and I can, of course, bound it by 2g times square root of q because of the Riemann hypothesis. And this important bound is called Haas-Veil bound. So we made them friends again, the German and the French guy. Okay. One example also maybe how we are going to use it. So let's take an elliptic curve over f7 given by y squared equal x cubed plus 2. Okay, I mean this is the affine equation. If you want the projective one, you add a z here and a z cube here. If you do the count, replacing each value of x in f7 and see, I mean, if this expression is a square, and not forgetting the unique point at infinity, you find that the number of points of E over f7 is going to be 9. But, I mean, by the formula that we just saw over there, this should be also 1 plus 7 minus alpha 1 plus alpha 1 bar, right? Which says that the ft I'm looking for is completely now determined because f of t for a genus 1 curve should be just 1 minus alpha 1 t, 1 minus alpha 1 bar t. So this is 1 minus alpha 1 plus alpha 1 bar t plus alpha 1 times alpha 1 bar. I mean, this is q because the norm is q. And so that's qt squared. And we have just seen that, so this is 8, which means that this was minus 1. So it should be 1 plus t plus 7 t squared. All right. But also what is nice is that if you want to know now, for instance, the number of points on E over f7 square, I mean, of course, you could take all points in 7 square, f7 square, and try them. But you don't need to, because now you can use this formula that we have here, that the number of points is going to be 1 plus 7 square minus alpha 1 square plus alpha 1 bar square. But of course, this is 50 minus alpha 1 plus alpha 1 bar square minus 2 alpha 1 bar. So this is 50 minus, so this was minus 1, so it's 1 minus 2 times 7 is 14. So you get that the number of points is going to be 63. You see, very easy and much faster to compute in this way. Okay, and as an exercise maybe, let me write it here for you. So prove that the zeta function of C over fq to the n. So C is a curve defined over fq. And now you would like to see the zeta function of the curve but seen over an extension of degree n in T. That this is going to be, so 1 minus T, 1 minus q to the n T. And here what you have to do is replace this by the product from n equal 1 to g of 1 minus alpha I n T, 1 minus alpha I bar n T. Okay. I leave it to you as an exercise. As maybe an interlude, let me also say, nice, so we have this important zeta function. We know that it is a rational function, and we would like to compute it for a curve. I give you an equation of a curve, and it tells you now over finite fields, and I tell you, okay, this is a curve of genus G, let's say G equal 6. And can you compute the zeta function? How would you do? Well, I mean, you could simply take more or less the definition. What I said, I mean, it would be enough to compute the number of points over every extension up to the 2G equation extensions, which means that for a curve of genus 6, you would have to compute the number of points over fq, fq squared, fq cubed, up to fq to the 12. And how do we compute a number of points over fq? Well, you take, if you have no like smart ways of doing it, you take the equation of your curve inside some projective space and you try all the points on the projective space and you see if it satisfies or not the equation. So if your curve, let's say, is inside some p to the n, okay, it means how many points to try. How many points do you have in Pn over fq? Or fqi, let's say in general. I mean, roughly, this is going to be q to the ni. And I said, I mean, you have to go up to 2g, or even like maybe g, I mean, if you take into account that if you know alpha I, you know alpha I bar, so what you need is only to determine really n numbers, n roots. So let's say you have to go take I up to G. So at worst, you will have a number of points to try that would be q to the ng. And n, what is n in general? I mean, if you don't have any smart way to embed your curve inside a Pn with n small, let's say if C is non-hyperelliptic, you're going to take the canonical embedding. So n is going to be g minus 1. So again, I mean, n might be close to g. So you would have something that is q g to the square. Well, that's frightening, okay? Because, I mean, as soon as q is a bit big, this kind of things you can't try. I mean, it's too many possibilities. It's exponential in g, and it's exponential in the size of the finite fields, which is q. So, I mean, this is quite problematic. And people are interested in doing like this kind of computations, for instance, for crypto, for purposes for cryptography. So they have tried to do it. But right now, what is the current state? I mean, there are plenty of very smart and powerful algorithms. But except, I mean, if g equals 1, then you have fast practical ways to compute the zeta function. But in general, if G is larger than 1, you restrict it to Q, which are of the form, so P to the N, so P is the characteristic, with P small. So note that not necessarily Q is small. Q can be even quite big, but the characteristic has to be small. And otherwise, yeah, it doesn't work. And even if you take the current states of art, I mean, generally you can maybe go up to G equals 5 and over field maybe of F31, I mean P less than 31, let's say. That's how restricted it is. But it's already good. It's already quite good and enough for many purposes. Okay, so now this said, as I said, I mean, I want to give a proof which is not the usual proof that, I mean, you can find in my notes, and I will give the historical proof, the second historical proof by Veil itself, using intersection on C times C, and I will follow quite closely a note. So I will follow a note by Marc Indry, which is called, it's in French, La preuve par André Veil. De l'hypothèse de Riemann pour une courbe sur un corps fini. And actually what we are going to prove is only the third part. The two first parts were known before Veil. And also, we are not even going to prove that F is exactly of this form. We are going to prove this inequality. The Haas-Veil inequality here is what we are going to prove. And if you look at the notes of the course, you will see that in the lemma 6.1.4, there is the proof that if you prove only this kind of inequalities for any n or any sufficiently extensions, then you can also prove that F is exactly of this form that we have here with the right norm on the roots. So that's exactly what we have to prove. And in order to do it, we are going to use intersection theory on C times C. And, well, either you're familiar with intersection theory, and then it's fine. I mean, I will just recall some general results. Or you're not, and then, I mean, it's better than you stick to the proofs that are already in the notes. All right, so for the proof of this Riemann hypothesis, or more exactly the Haas-Veil bound, as I said, we will need intersection theory. So let me just start with a general result. So for S is going to be an algebraic smooth surface, so dimension 2, projective. And I will refer to the book of Archon, Algebraic Geometry, in chapter 5 for some of the results. So I mean, this is what is called corollary 1.8 in Archon. So if you have H, an ample divisor on S, and D, a divisor on S such that D intersection with H is positive, and such that D square, so the self-intersection is also positive, then there exists a N, or for any N, for all N sufficiently large, the divisor N times D is effective. So a positive, I mean a sum with positive coefficients of irreducible curves on the surface. And from this, I mean, the first important result is the Hodge index theorem, which is also in Archon, but it's not exactly the same form that I'm going to use. Archon uses something a bit different. I mean, it's theorem 1.9, and I'm going to give a version which is a bit weaker somehow, but enough for us. So H is an ample divisor, and D now is such that a divisor such that H times D is 0, then the self-intersection of D is non-positive. So in order to prove it, well, let's assume the contrary, so let's assume that D square is positive. Then, by ampleness, one knows that HM equals D plus MH is ample for M large, okay? And also, now if I compute D times HM, I mean, by hypothesis, D times H misses 0, so what is left is D square. So it's going to be positive. So I have something which is positive, and the intersection with D and ample divisor is also positive. So I can apply the corollary 1.8 by 1.8. I deduce that a multiple of D is effective. But then, because I mean this is true, it should also be the case that when I intersect D with H, I should obtain something which is also effective, I mean positive, because it should be an intersection of effective divisors. And one gets a contradiction. Okay, as an exercise, I also suggest that you look to prove, I mean, the following type of identity with the same hypothesis H ample and D a divisor, that D square times H square is always smaller than D times H square for any D. So, I mean, you can try. If you want a hint, I mean, I'm going to give one, so if you don't want a hint, just stop the video now, but if you want a hint, so the hint is to look at the divisor D1, which is H square D minus D intersection with H times H. Okay, consider this divisor and use the results above. All right. Now, I will go to an inequality which is called Castel Nuevo inequality. And this one is specific to the surface C times C. So here S now is going to be the product of C which itself. And I'm going to take D, a divisor on C times C. And P is just a point on the curve. I'm going to introduce two special divisors. So F1 is going to be C times P, and F2 is going to be P times C. Oh, sorry. P times C. And D1 is the intersection of D with F1, and D2 is the intersection of D with F2. And then Castel Nuevo inequality says that D squared is smaller or equal to do D1, D2. Okay, let's look at the proof. So here, it's somehow, you have two copies of C. So this is a copy F1, and this is the copy F2, and obviously this is going to be the point with coordinate PP. So just looking at this somehow, you already observe that the intersection of F1 and F2, it's 1. It's only the point with coordinate PP. More interestingly, what is the self-intersection of F1? Well, in order to do this, you must remember that self-intersections, they don't change if you change one of the divisor up to linear equivalence. But now, clearly one divisor which is going to be linearly equivalent to this one is a translate that would pass through a point Q that is different from the point P. And of course, if you do this, what you observe is that then you get somehow two parallel curves, and so the intersection is now empty. So F1 square is actually 0, as is F2 square. Okay. Now, what else do I need? I would need some ample divisor, and what I pretend is that H, which is the sum of F1 plus F2, is ample. For this, I'm going to use Nakai-Moiseno criterion, which is also in Archon. And you have to verify first that F1 plus F2 square, and you can easily compute because you have all these formulas here. This is 1, so this is positive. And if X is any irreducible curve on C times C, you want to compute X times F1 plus F2. And I say that this is also going to be positive because, you see that the projection of X on F2 and on F1 can't be constant at the same time. And if it's not constant, it means that it needs to intersect the curve F1 or F2 in at least one point. So if this is the case, then it means that this is also going to be positive. And because of this, and applying this criterion, you see that indeed H is ample. Okay, now I have all the ingredients to apply the previous result. So let D1 equals D minus D2 F1 minus D1 F2. So what do I observe? That if I do D1 times H, if you compute it, this is 0. So I have an ample divisor H. I have a divisor such that the intersection is 0. I must conclude from this that D1 square is negative, but if you do the computation with D1 square, what you get is D square minus 2D1 D2, and you have the result. Okay, now we move even closer to our topic because now as far as we concern, I mean, we had S, an algebraic surface over any field. Then, I mean, we restrict it to S, C times C, but I'm still over any field. And now I'm going to move to C times C over a finite field. So let gamma be the graph of the Frobenius map from C to C. So I'm going to say more exactly what it is. So if I take now a projective embedding of C in some projective space, then I can look at a point X, at a point P, sorry, with coordinate x0 up to xn. And this map is simply the map that to P associate x0 to the, if I'm over, so I'm a curve over fq. So C, sorry, let me remind that is a curve over fq. So it's going to be x0 to the q, xn to the q, okay? And this is what we call, I mean at the beginning of the course also, the Galois conjugate of P for the arithmetic Frobenius automorphisms of the finite field. So I sometimes denote it with a sigma, where sigma is going to belong to gal of fq bar over fq, and it's just sigma of x is x to the q. Okay, so I have this. Delta is going to be the diagonal. And then I want to compute a bunch of things. So f1 and f2 are still going to be like a first copy and a second copy of C. So first I say that if I do the intersection of the graph of the Frobenius with the diagonal, and I compute this intersection, this is what we are looking for, meaning the number of points on C over fq. Why so? Well, simply look what it means to be on the graph. I mean, to be on the graph is a point P sigma. But what does it mean to be on the diagonal? It means that P is equal to P sigma. But if P is equal to P sigma, we know, I mean, that means that all coordinates have to be rational, so the point is rational. So what you're counting when you're counting this intersection is the number of points on C which are rational, meaning this cardinality. So this is okay. Now, if I intersect gamma with f2, what I get is 1. Because, yeah, I mean, this is a function. So when I have a point, there is only one image. And so this is exactly what this counts. The intersection of gamma with f1, I mean, this is more or less, now I have a point, and I want to know the number of pre-images. And, I mean, it's a bit complicated because, I mean, this map can be seen like, I mean, it's not necessarily separable. But even, I mean, we know that this Frobenius map have degree q. So this counts actually the degree of the map. So this is q. Okay. And now comes the tricky part. Which is to understand the self-intersection of the diagonal. So, and I pretend that the self-intersection of the diagonal is 2 minus 2g, where, so g is a genus of C. Okay, so first, I mean, we need like, so that's the proof inside the proof. We need a result which is called the Junction Formula, which is valid for any surface S. Which tells you that if you take a divisor, a non-singular curve, so an X, a non-singular curve, on S, then 2g minus 2 is x squared plus x times k of s, so this non-singular curve on S of genus G, and ks, this is the canonical divisor on S. Okay? But now, for the particular case where S is C times C, I can take the canonical divisor as P1 star of K on C plus P2 star K of C, where P1 is the projection on the first component and P2 is the projection on the second component. Okay? All right. So let's use this beautiful formula with x going to be the diagonal delta. So 2g minus 2 is delta square plus delta times k C2. So that's what we are looking for, and now we have to compute this. But if I take, k of C is a divisor on the curve. So it's just a sum of, we know, the degree of k of C, it's 2g minus 2, so it's the sum of 2g minus 2 points. So it's like when I do P1 star, I'm going to lift 2g minus 2 copy of C. So, and if I intersect the diagonal with 2g minus 2 copy, this is exactly just 2g minus 2. And, well, sorry, let me rephrase that. So this is delta square plus delta times P1 star of Kc plus delta times P2 star of Kc. So as I said, this is 2g minus 2, and for the same reason, this is again 2g minus 2. So if you put it in the other way, you get indeed the formula that delta square is 2 minus 2g. Okay? And, right. Now, because, this is maybe a tricky part, I would like also to give you how you can find this result, but on a particular example. So, I think it might be quite instructive to see it not in full generality, but on an example how you can try to understand also this computation. So let me take example. So C is going to be a hyperelliptic curve with f of degree 2g plus 1. So there is a unique point at infinity. On the non-singular model of C, we have seen already these results. There is a unique point over the point x at infinity. So I call it still infinity. And I can take, for instance, 2 points. So let me plug x equals 0. So f 0 and so 0 square root of f0 and 0 minus square root of f0. These are going to be 2 points that I call q1 and q2. And infinity is the point infinity on the non-singular model. Okay. And what I say is that if you look at the divisor of x, well, it's going to be exactly q1 plus q2 minus 2 times at infinity. This is just some classical computation with divisors, as we have seen in the previous chapters. And now, let f, the function on C times C, which is given by, so to k, and which at the point P and Q associate x of P minus x of Q. So what can we say about the divisor of such a function? So the divisor of f, obviously, this is going to be 0 when P is equal to Q. So inside the divisor of x, you have the diagonal delta. But you have also the case where maybe Q has the same x coordinate, but minus y as the second coordinate. So what you have is also a copy that I call delta bar, which is the graph of the involution xy goes to x minus y on C. And then you have also the contribution at infinity, so 2 times infinity times C minus 2 times C times infinity. Okay? So now, because this is an effective divisor, so if I do the intersection of div of f with delta, I should get 0. And if I compute now with the right member, I obtain delta square plus delta times delta bar and minus, so delta times this, but already we have computed this once. I mean, this is 1, so it's minus 2, and minus 2, so minus 4. So the only piece I need to understand is this middle term. But now what it means, I mean, this is going to be equal to what? You want points that have the same x coordinate and the coordinate such that y is equal to minus y. So at least if the characteristic is different from 2, and of course as I took this kind of model, I assume that the characteristic of k is different from 2. This is going to be the case only if y is equal to 0. So the point of intersection of delta and delta bar are the points which are the Weierstrass point or the zeros of f. Okay, so how many do you have? I mean, apparently you have 2g plus 1, but you shall count also the point at infinity as 1. So that's you 2g plus 2 we were looking for, and we are happy because we get again the same formula. Okay, let me finish now with the proof. Let me see here. Okay. So we have to now apply these computations to a divisor D, which is going to be R times gamma plus S times delta. And so R and S are element in Z. So I denote, as I did before, D1 is D times F1. So it's going to be, with the computations we have done, RQ plus S, and D2 is going to be D times F2 by definition, and this is going to be R plus S. So what does Castel Nuevo inequality implies? it implies that d square so which, if I do the computation, is going to be r square q 2 minus 2g plus 2rs cardinality of c over fq plus s square 2 minus 2g is smaller or equal to 2 times d1 d2, so 2 times rq plus s times r plus s. And actually, if you look carefully, I mean, I forgot to tell you something, because when I compute d squares, then I have also to compute the self-intersection of gamma, which itself, that I haven't done here. And so the self-intersection of gamma, which itself, you can do it in the following way. You have to see that the divisor gamma is the pre-image of the diagonal by the Frobenius map. So then there is a formula that tells you that when you compute the self-intersection of gamma with itself, it's going to be the degree of the map, so Q, times the intersection of the delta with the diagonal which itself. So we had already know that intersection of delta which itself is 2 minus 2g. The degree of the map is Q, so gamma square is Q times 2 minus 2g. Yeah, I forget to mention it, but it's really another general result on like intersection numbers of pre-images of a divisor. Okay, and now you change a bit, you move everything around, and what you see is that you get gq r square plus q plus 1 minus the number of points c over fq rs plus gs square is greater or equal to 0, which means that if you look at this as an equation, homogeneous equation in R and S, you want the discriminant of this equation to be negative, because otherwise it would have zeros. So you want it to be, well, or at least non-positive. So it means that this minus q plus 1 is less or equal to 2g square root of q. Okay, we found it. Wow, so it was quite a lot of manipulations of divisors, not super easy. I mean, as I would say, the proof we have inside the notes is much more elementary. It's also tricky. I mean, there are also tricks. I mean, you don't get such a powerful theorem for free. I mean, you have to, I mean, if you get something for free, probably it's not valuable. And this applies also to the real world sometimes. So, yeah, so be careful with that. And the other thing is, what I wanted to say is that the end of the proof may look a bit like, okay, what are these ugly manipulations, like plenty of variables and everything? And you're right. I mean, maybe there is a more like, let's say, self-explanatory way to try to prove this. And that's what, if you're curious, you can have a look at an article from Perret and Allouin, which is called From Hodge Index Theorem to the number of points on curves over finite fields. Because they show that the Hodge index theorem, I mean, at least a bit more powerful one, which is inside the Archon's book, give you that there is a space on which you have like a kind of scalar product. And this result is just a consequence of the fact that you have a scalar product on this space, and that you have some Gram matrix and you're taking the determinant of some Gram matrix. So it's much more conceptual, and because it's much more conceptual, it helps you also not to get only this inequality, but also plenty of other equalities that we are going to see in the next course. Thanks a lot for your attention, and yeah, see you for next class.